Bismillahirrahmanirrahim. Assalamu alaikum, students. Now, in the last lecture, we did a sample problem in which I will refresh your memory, in which we had 2 mole of an ideal gas, and that 2 mole of an ideal gas undergoes isothermal expansion along 3 paths. The paths were like this, PV diagram. I will not specify the values. I want to give you the idea. One path was like this. We call that path 1. And this path 1 was reversible. Then there was second path. This was second path. This was path 2, single step path. It was irreversible. And then there was also path 3, like this. This was path 3. Right? So we had path 1, reversible isothermal expansion, then path 2, irreversible constant pressure expansion, and then path 3 was 2-step irreversible process, and we are supposed to calculate the work done by the gas. And we solved for the values of work. Value for work for path 1, W was 19.3 into 10 raised power 3 joule. For part 2, the single setup part 2, the value of the work was, we wrote it W single, it was 9.23 into 10 raised power 3 joules. And for part 3, which is 2-step irreversible process, W 2-step, it was 12.9 into 10 raised power 3 joules. So for reversible isothermal expansion, work is 19.3 into 10 raised power 3 joule. For single step irreversible process, it is 9.23 into 10 raised power 3 joules. And for 2-step irreversible process, it is this value, 12.9 into 10 raised power 3 joule. So we concluded from this sample problem that the magnitude of work is greater for the 2-step process than for the single-step process, but less than that for the reversible process. Right? Now, this sample problem suggests that the magnitude of work for a multi-step expansion process increases with the number of steps. I repeat, because the work in single step process is 9.23, when you do the work in two-step process, it increases, it becomes 12.9 into 10 raised to the power 3 joules. So it suggests that the magnitude of work for multi-step expansion process increases with the number of steps. This indeed is the case. Imagine that the number of steps n increases so imagine that the number of steps n increases, n is here, number of steps. So if this number of steps n increases indefinitely, what would happen? Indefinitely. What would happen? As n increases, the pressure difference. Which pressure difference? P external minus P. P is the gas pressure, P external is the external pressure. So as n increases, the pressure difference P external minus P for each individual step decreases. I repeat, as n increases, where n is the number of steps, the pressure difference P external minus P for each individual step decreases, right? So in the limit, that n tends to infinity, the pressure difference, the external minus P approaches 0, right? And the total area of the rectangles, remember the area under PV curves the work. So this area under these rectangles, one area was this, one second area is the end area under the reversible process. Then we have another area under this black curve. So as n increases, then the area under these rectangles approaches the area under the reversible curve, right? Therefore, the irreversible process becomes reversible and the value of the work equals that of the reversible process, right? By contrast, if you take the case of compression work, the magnitude of the irreversible compression work exceeds that of the reversible process for finite values of n and becomes equal to that of the reversible process as n approaches infinity. Remember, here we're expanding the gas. Now I am telling you about the compression case. I am saying the magnitude of the irreversible compression work exceeds that of the reversible process for finite values of n being the number of steps. And this magnitude of irreversible compression work becomes equal to that of the reversible process as n approaches infinity. The difference between the expansion and the compression processes results from the requirement that P external is less than P at the beginning of each expansion step, whereas P external is greater than P at the beginning of each compression step, right? The conclusion is, what is the conclusion? W reversible is greater than or equal to W irreversible. This is for expansion step, right? Magnitude of the work done by the gas in reversible path is greater than or equal to the magnitude of the work done by the gas in irreversible path, right? By contrast, for the compression step, when you are compressing the gas, we have magnitude of W reversible is less than or equal to magnitude of W reversible, right? You have to remember this. For expansion step, magnitude of reversible work is greater than or equal to magnitude of W irreversible, right? For compression step, magnitude of reversible work is less than or equal to magnitude of W reversible. Sorry, it is here irreversible, IR, right? Irreversible. So the reversible work is the lower bound for the compression work, right? And the upper bound for the expansion work, right? What am I saying? The reversible work, I should write it. The reversible work is the lower bound for the compression work and the upper bound for the expansion work. I repeat, the reversible work is the lower bound for the compression work and the upper bound for the expansion work. This result for the expansion work can be generalized to an important statement that holds for all forms of work. I repeat, this result for the expansion work can be generalized to an important statement that holds for all forms of work. What is that result? Result is the maximum work that can be extracted from process between the same initial and final states is that obtained under reversible conditions. Very important result. I repeat, the maximum work that can be extracted from a process between the same initial and final states is that obtained under reversible conditions. Remember when we started the last lecture and we solved this sample problem, we said we have to establish a result in thermodynamics, which is important. This is the result which we wanted to establish through the sample problem. So let us move to our next topic. Our next topic is how to determine delta U. Right? How to determine delta U? What is delta U? Change in internal energy. Right? So how we determine it for a thermodynamic process? Should write it for a thermodynamic process, right? I will give you the idea. You know the statement of first law. From first law of thermodynamics, dq is du plus dw. Remember, we are using the convention for work. Positive work means work done by the system, and negative work means work done on the system. That convention we are using. Now imagine the process is carried out under constant volume conditions. Let me write it. Imagine the process, the thermodynamic process for which we have to calculate the change in internal energy, imagine that process is carried out is carried out under constant volume conditions and that non-expansion work is not possible, right? Remember, we have already discussed that there are two kinds of work, expansion work and non-expansion work. So we're assuming the process under question is taking place at constant volume and there is no non-expansion work possible. So we have only expansion work. Then under these conditions, our work Tw is 0. Because expansion work under constant volume conditions is 0. When volume is constant, change in volume is 0, so expansion work is 0. Remember how we write expansion work? Integral P external dV. So if dV is 0, this work is 0. So what we get from first law, we get dq, but which dq? Under constant volume conditions. So I put subscript V. So dqv is heat put into the system at constant volume is equal to du. So I encircle this equation, it is important. I name it equation 1. Now this equation 1 states equation 1 states that du, that is change in internal energy, can be experimentally determined by measuring the heat flow, between the system and surroundings in a constant volume process. Right? So this is how we determine change in internal energy of it for some thermodynamic process of some system. Right? Now we want to define another quantity called enthalpy. Enthalpy is denoted by H. There's also a state function. So I write a new state function. Let us see how we define it. First, we want to see how can we write first law under reversible and constant pressure conditions. See, the first law of thermodynamics, that is this one, dq equal to du plus dw, can be written under reversible and constant pressure conditions as and constant pressure conditions as. So we write du, let me first, if I write it, you can write it du equal to dq minus dw. I took this term to left hand side. So I get du is dq minus dw. Now I can write it du is dq subscript p, where subscript p indicates that the conditions are constant pressure conditions, right? Then you write minus P external dV, because P external dV is dW. But you have another condition to put in, reversible condition, where we said that conditions are reversible. Then I can write it dq of P minus PV, because for reversible process, P external is equal to P, right? External pressure and the system pressure is equal for reversible process. So this is our first law written for constant pressure and the reversible conditions, right? We can integrate this expression between the initial and final states. So integrating between the initial state I and final state F, what we get integral I to F du, which will be uf minus ui, which is equal to integral dq p minus integral dV, right? And limit of integration are I to F, I to F. Since internal energy is state function, so integral dUI to F is simply UF minus UI, UF being the internal energy in final state and UI being the internal energy in initial state. So what I get UF minus UI. When I integrate this heat, it is just total heat put into the system at constant pressure, or total heat which moves across the system and surroundings at constant pressure, right? This is simply P F VF minus PI VI. And since in this case PI is equal to PF is equal to P, here pressure is constant. So you know PI is equal to PF is equal to P, right? So this is our functional relationship. So, but we keep it as PF VF minus PI VI. Let me name this equation, or I'm directly rearranging we get. Rearranging we get. If you rearrange the above equation, you will get UF plus PF VF minus UI plus PI VI is equal to P. See how UF, here you have a term on the right hand side minus times PF VF. It goes to the left hand side, it becomes plus PF VF. So we have UF plus PF VF term on the left hand side. Then you have on this side minus UI. You take this minus times minus is plus PI VI to the left hand side, which becomes plus PI VI. So we have another term UI plus PI VI, and what remains on the right hand side is QP, right? Now, because P, phi, and U are all state functions, so I write because P, V, and U are all state functions, U plus P is a state function, right? Now this U plus PV is called enthalpy H, right? So enthalpy H is defined as U plus PV. This is the definition of enthalpy. So what is then this equation telling us? It is HF minus HI, which is delta H, equal to QP. It's another important result. What is HF? Enthalpy in final state. HI is enthalpy in initial state. So delta H is a change in enthalpy. So this equation is telling us delta H equal to QP. Let me name the previous equation. It is equation 1. So let us name it equation 2. So this equation 2 is telling us what? It is telling us that for a process involving only PV work, we can determine the enthalpy change by measuring the heat flow between the system and surroundings at constant pressure conditions. So I write therefore delta H for a process involving only PV work can be determined by measuring the heat flow between the system and surroundings at constant pressure, right? So you can see that equation 2, which tells us how to determine the enthalpy change delta H, is simply constant pressure analog of equation 1, right? Another thing, what about the unit of enthalpy? Like internal energy, enthalpy has units of energy, right? It has unit of energy. Let us move to next thing. Remember the statement of second law of thermodynamics in terms of entropy. As you know, how we introduce the second law of thermodynamics, we first discuss second law of thermodynamics' importance. We said there are processes which could take place in nature by conserving energy. That means by complying with the first law of thermodynamics, but they still don't occur. And we said there must be some other law which is second law of thermodynamics, right? I want to refresh your memory. I write, we've already discussed this. I want to just refresh that. The universe has a natural direction of change. Remember when we stated second law of thermodynamics in terms of entropy, we said the entropy of the universe is greater than or equal to, a change in entropy of the universe is greater than or equal to zero, and equality holds for reversible processes. So for all irreversible processes, change in entropy is positive. And when we say this change in entropy, remember this change in entropy is the sum of changes in entropy of the system and change in entropy of the surroundings or environment, or sometimes we say change in entropy in the universe. So I refresh that. Then we discuss the arrow of time. So that arrow of time tells us the natural direction of a change. As I want to refresh that, we said first law of thermodynamics states that in any process, the total energy of the universe remains constant. And you know that the first law requires that a thermodynamic process conserve energy. It does not predict which of several possible processes will occur. Consider, for example, the following two examples. If we have a metal rod, we've already discussed it. I'm just refreshing you. If I have a metal rod initially at a uniform temperature, initially at a uniform temperature, so throughout initially it has same temperature, this metal rod in principle could undergo a spontaneous transformation. Spontaneous transformation means, we will explain that, in which one end becomes hot and the other end becomes cold without being in conflict with the first law, as long as the total energy of the rod remains constant. However, experience demonstrates that this does not occur, right? Similarly, if we have an ideal gas, that is, if you have some ideal gas, that is uniformly distributed in a rigid adiabatic container, that means it is adiabatically isolated, it could undergo a spontaneous transformation such that all of the gas moves to one half of the container, leaving a vacuum in the other half, right? Because for an ideal gas, you know, internal energy dou U by dou V at constant temperature is 0, right? For an ideal gas, we know dou U by dou V at T is 0. The energy of the initial and final states is the same, right? So it does not violate first law. I repeat, if we have an ideal gas in a rigid adiabatic container, it could undergo a spontaneous transformation such that all of the gas moves to one half of the container, leaving a vacuum in the other half without violating the first law of thermodynamics. But this transformation doesn't occur. So both of these transformations, whether we did, which we talked about, the metal rod and the ideal gas situation, both of these transformations neither occur, even when they are in accordance or in compliance with the first law of thermodynamics. So experience tells us that there is a natural direction of change in these two processes. What is that natural direction? A metal rod with a temperature gradient always reaches a uniform temperature at some time after it has been isolated from a heat source, right? That is the natural direction. I said, if I have a metal rod with a temperature gradient, that one portion of the metal rod has temperature T1, other portion of the rod has temperature T2. If T1 is greater than T2, T2 can be greater than T1, but let us assume T1 is greater than T2. What is the natural direction for this metal rod? If it has been isolated from a heat source, what would happen to it? It would reach a uniform temperature at some time after it has been isolated from a heat source. Similarly, a gas confined, if you have a gas, we confined it to one half of a container with a vacuum in other half, right? It would distribute itself uniformly throughout the container if the value, this value separating the two parts is opened, right? Now the transformations described can be, the transformations can be unnatural transformations. The previous ones, these transformations, when we said if we have a metal rod, it's which is initially at a uniform temperature, its one end can become hotter, other end can become colder, or this ideal gas uniformly distributed initially could move to one half of the container and create vacuum in the other half of the container without violating the first law. Now, these two transformations never occur in nature, so they are called unnatural transformations. Unnatural transformations, right? The word unnatural is used to indicate that in many human lifetimes, these transformations do not occur. I should write it. The word unnatural is used to indicate that in many human lifetimes, these transformations do not occur, right? You need to remember, it is important. By contrast, the reverse processes, right, in which the temperature gradient along the rod disappears and the gas becomes distributed uniformly throughout the container, they are natural transformations. Natural transformations, right? Also called spontaneous process. This was my important thing. These natural transformations are, let's use another color, are also called spontaneous processes, right? Spontaneous processes. Then what is a spontaneous process? A spontaneous process is one that, if repeated again and again, again and again over the course of a human lifetime, leads to the same outcome. Very important statement. A spontaneous process is one that, if repeated again and again over the course of a human lifetime, leads to the same outcome. So you can understand from these definitions, we said unnatural is used to indicate that in many human lifetimes, these transformations do not occur. So that means we do not say that these unnatural processes cannot occur. We're only saying that the probability of occurrence for these unnatural processes is exceedingly small. And the probability of occurrence for these natural processes, transformations, or spontaneous processes are, the probability is exceedingly large, very large, right? We have already discussed how to calculate the entropy change for a reversible or irreversible process. Now, we know that the entropy of the universe, the total change in entropy of the universe, is greater than or equal to 0, and equality holds for a reversible process. So we want to make a statement about isolated systems. Remember, when we talk of this, we're considering an isolated system. So let us state this, refresh this important result. I write, for any irreversible process in an isolated system, there is a unique direction of spontaneous change. What is that? Delta S greater than 0 for a spontaneous process. Delta S less than 0, that means decrease in entropy for the opposite or non-spontaneous. So you can see we use the word non-spontaneous process for unnatural process. Non-spontaneous direction of change. And delta S equals 0 only for a reverse process. Only for a reversible process. Right? So in a quasi-static reversible process, there is no direction of spontaneous change because the system is proceeding along a path, each step of which corresponds to an equilibrium state. Remember this statement forever. I repeat it: for any irreversible process in an isolated system, there is a unique direction of spontaneous change. Which is that direction? Delta S greater than 0 for a spontaneous process. Delta S less than 0 for the opposite or non-spontaneous direction of change. And delta S equal to 0 only for a reversible process. So in a quasi-static reversible process, there is no direction of spontaneous change because the system is proceeding along a path, each step of which corresponds to an equilibrium state. We have discussed this already. I'm just emphasizing or refreshing your memory, emphasizing the results again and again. Right? There's another result called the Clausius inequality. Let us do that. So my another result is the Clausius inequality. Now, we already discussed using two examples that delta S greater than 0 provides a criterion to predict the natural direction of change in an isolated system. For any isolated system, the natural direction of change is that change for which delta S is greater than 0. Now, this result can also be obtained without considering a specific process, right? So we want to do that. We want to obtain the same result without considering a specific process, right? So consider the differential form of the first law. Use another color. Consider the differential form of the first law for a process in which only the work is possible. So we have what? We have du is equal to dq minus p external db. Let me name it first. So now this equation first is for this particular topic, Clausius inequality. Don't mix it with the previous equations. So we had already equation 1, 2. Forget that. Now this is equation 1 under this particular heading, the Clausius inequality. So we have written the differential form of the first law for a process in which there is only PV work possible. This equation 1 is valid right here. Valid for both reversible and irreversible processes, right? Because we are writing pressure as P external and we are not specifying dq, right? If the process, we specify now, if the process is reversible, we can write equation 1 as, how we write it? du is equal to dq, we write subscript reversible, right? It specifies that heat is put into the system or heat moves across the boundary between the system and the surroundings under reversible conditions, right? And we write then PD. This is for reversible process, P external is equal to P. And we know from the definition of change in entropy, you know ds is dq reversible over T. So you can write, therefore, for dq reversible TdS. I can write it, therefore, is equal TdS minus PD, right? Let me name it equation 2. It is my equation 2 now. Now, because u is a state function, du is independent of the path, and equation 2 holds for both reversible and irreversible processes. Let me write it, because it gives me change in internal energy. Because u is a state function, du is independent of the path, independent of the path, and equation 2, this equation for du, holds for both reversible and irreversible processes, as long as there are no phase transitions or chemical reactions, and only PV work occurs. These things we have already discussed, that when we write first law as dq is equal to du plus dw, it is assumed that there are no phase transition or chemical reactions taking place. Now in this discussion, we are assuming only PV work occurs. Now to derive the Clausius inequality, what we do to derive the Clausius inequality, we equate the expressions for du in equations 1 and 2. We have two expressions for du. One is this, equation 1, second is this, equation 2. Both are valid for both reversible and irreversible processes. So we can equate them. When you do that, you get, I will do directly, you can check it. You'll get, let me use this color. You will get dq reversible minus dq equal to p minus p external times dv. Right? dq reversible minus dq is equal to p minus p external times dv. We name it equation third. This is my equation third. I've used 1 and 2. Now this equation third. Now if p minus p external is greater than 0, that means system pressure is greater than the external pressure, the system will spontaneously expand. The system will spontaneously expand. That means its volume will increase, and that means change in volume is positive. dV is greater than 0, right? And if p minus p external is negative, that is less than 0, the system, because p external then is greater than p, what will happen? System will spontaneously contract. The system will spontaneously contract. When it contracts, change in volume will be negative. That is, dV is less than 0. I repeat, if p minus p external is greater than 0, the system will spontaneously expand and dV is greater than 0. And if p minus p external is less than 0, the system will spontaneously contract and dV is negative. So in both cases, whether the system contracts or expands, you should write in both possible cases, what will happen? P minus P external times dV is greater than 0. In first case, P minus P external is positive, dV is positive, positive times positive is positive. In second situation, P minus P external is negative, dV is negative, the product negative times negative will be positive. That means for both cases, this right hand side is positive, right? Therefore, we conclude therefore we conclude that dq reversible minus dq. Instead of dq reversible, I can write tds minus dq is greater than or equal to 0. Greater than possibility is for both cases. My right hand side is positive. So this difference is positive, and equality when the process is reversible, right? Let me name it. This is my equation 4. This is my equation 4. Right? The equality holds when dq and dq reversible are equal. That is, process is reversible. Right? You should mention the equality holds only for a reversible process. This equation four, TDS minus DQ is greater than 0. It is called Clausius inequality. Inequality. Right? We rewrite the Clausius inequality in equation 4, that is this equation, for an irreversible process in the form for an irreversible process in the form. We have to remove the equality for an irreversible process. But we write ds is greater than dq by t. See, we take this dq to the right hand side. What you get, dq is less than tds, or you can write dq by t is less than ds, or ds is greater than dq by t. Let me name it equation 5. Right? However, for an irreversible process in an isolated system, that's a special case. The system is isolated. However, for an irreversible process in an isolated system, the Q we put in the system is 0. Therefore, If it is systemized, this is 0. Therefore, we have proved that for any irreversible process in an isolated system, delta S is greater than 0, right? Because when you put dq is 0, ds would be greater than 0 for an isolated system. So we have built for an irreversible process in an isolated system. Delta S is greater than 0, positive, right? Next, we can use the Clausius inequality to evaluate. We can use the Clausius inequality to evaluate the cyclic integral. Which integral? Closed integral dq by t for an arbitrary process. So what we do next, we use Clausius inequality to evaluate the cyclic integral, closed integral dq by t for an arbitrary process. Remember, because ds is equal to dq reversible over t, the value of the cyclic integral is 0. The value of the cyclic integral, that is this integral, is 0 for a reversible process. If you want to find for an arbitrary process. Now, for that, consider a process in which the transformation from state 1 to state 2 is from state 1 to state 2 is reversible. but the transition, but the transition from state 2 back to state 1 is irreversible. Therefore, we can write closed integral dq by t and break it into two parts. We are going to state 1 to 2 first. That is reversible. So I write dq reversible over t, plus we come back to complete the cycle 2 to 1. But we are saying that this transition is irreversible. So I write irreversible over t. 1 to 2 dq reversible over t plus 2 to 1 dq irreversible over t. Now the limits of integration on the first integral can be interchanged, to obtain closed integral dq by t minus times 2 to 1 dq reversible over t plus 2 to 1 dq irreversible minus times 2 to 1 dq reversible over t plus integral 2 to 1 dq irreversible over t. Exchanging the limits as written is only valid for a state function. Remember, this is a state function. For a state function, we can do such thing. We can write it negative times, then exchange the limits from 1 to 2 to 2 to 1. Right? Now, because dq reversible is greater than dq irreversible, right? dq reversible is greater than dq irreversible. That means what? Is greater, this is smaller. That means negative term will be bigger. Overall, it will be negative, right? Closed integral dq by t will be less than 0, negative or equal to 0. Let me name it some equation. Equation 6. It's my equation 6. Let me encircle it. Where the equality only holds for a reversible process where the equality only holds for a reversible process, right? And you might notice that the cyclic integral of an exact differential is always zero, but the integrated integrand in equation 6 is only exact differential for a reversal sign, right? So we have solved for this cyclic integral for an arbitrary process. So you need to remember this inequality also. Let me summarize today's lecture, what we did, and we will move forward. We started with this previous sample problem. So from that sample problem, we made this result, we justified this result or established this result. The maximum work that can be extracted from the process between the same initial and final states is that obtained under reversible conditions, right? Then we said how we can determine change in internal energy for a thermodynamic process. Simply, we have to measure the heat flow between the system and the surroundings at constant volume conditions, right? And we defined our new state function enthalpy, H, which is defined as P plus U plus PV. This was the defining equation. We said its units are and that of energy. And we said how to determine the change in enthalpy simply by measuring the heat flow between the system and the surroundings at constant pressure. Then we said the universe has a natural direction. We said there are some processes which are called natural processes, some are called unnatural processes. We gave examples of, we discussed the metal rod initially at uniform temperature and the ideal gas initially uniformly distributed in an adiabatic enclosure. And we discussed that the processes can be unnatural or non-spontaneous. Let me write or non-spontaneous. What are those processes? I said unnatural word is used to indicate that at many human lifetimes, these transformations do not occur. On the other hand, natural transformations, which are called also spontaneous processes, how we define them, if these are those processes, if repeated again and again over the course of a human lifetime, lead to the same outcome. Then we refreshed our second law of thermodynamics in terms of entropy, and we made this important statement. We said for any irreversible process in an isolated system, there is a unique direction of spontaneous change. Delta S is greater than 0 for a spontaneous process and negative for a, or the opposite or non-spontaneous process direction of change, and delta S is 0 only for a reversible process, right? Then we talked about Clausius inequality. And we derived it. So Clausius inequality is in general written as This is TDS minus DQ is greater than or equal to 0, or you can write TDS is greater than or equal to DQ. Then we said equality holds for reversible process. For irreversible process, you remove the equality, you write ds is greater than dq by t, and if the process system is isolated, dq is 0, and for irreversible process and isolated system, ds is positive, right? Then we derived this cyclic integral. We said closed integral dq by t is less than or equal to 0, equality holds for reversible process, right? So this is all for today. Prepare your exams, don't waste your time, listen to all video lectures carefully, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.